As you may recall, double displacement reactions involved two compounds, A, B, and C, D, where each of those was an ionic compound. So A and C are both cations, and B and D are both anions. And the two compounds could switch partners as long as the bonds in the new compounds were stronger than those in the previous ones. Single displacement reactions differ from double displacement reactions in that instead of two compounds, we have an element reacting with a compound, forming a second compound and another element. So in this case, A takes the place of B, and B then becomes a neutral element. If A is a metal, it's going to switch places with B, which is the other metal, and so A will end up bonded with nonmetal C, and metal B will end up by itself. If A is a nonmetal, then it's going to trade places with C, which is the other nonmetal, and then metal B and nonmetal A will form a new compound, and nonmetal C will end up by itself. All right, now let's take a look at an actual example. In this case, we have magnesium is a metal, so it's going to trade places with calcium, which is also a metal. So the magnesium and calcium will switch places. Since magnesium and calcium are both in group 2 and they both form positive 2 ions, the magnesium is also going to have 2 chlorides, and then the calcium will be replaced. If we have a nonmetal element rather than a metal element, then the nonmetal will trade places with the nonmetal. So fluorine is going to switch places with chlorine this time. And again, since calcium and fluorine are both in the same group, the calcium is going to have 2 fluorides, just like it had 2 chlorides, and we'll end up with Cl2 as our other product. Keep in mind that chlorine, like several other elements we've talked about, always come in pairs. Oxidation and reduction reactions involve the gaining and losing of electrons. In a double displacement reaction, the charges of the atoms remain the same because no electrons are being gained or lost, and that's one of the key differences with single displacement reactions. So the magnesium's charge starts out at 0. All elements are 0 to start with, and it ends up as a positive 2. The calcium started out as a positive 2 charge and ended at 0. The only way that an atom can change its charge is by gaining or losing electrons. So here's an important rule. If the charge on an atom increases, then that atom has been oxidized, or it's undergone oxidation. And so the magnesium, it went from 0 to positive 2. An increase in charge means oxidation. If the charge on the atom decreases, like it did with the calcium, that means reduction. And so that makes very good sense. If the charge decreases, then the atom was reduced. The chloride stayed the same. The charge didn't change, so just like we had back in double displacement reactions, we refer to the chloride here as a spectator ion. So a redox reaction simply means we have oxidation and reduction. One atom always has to be oxidized. In that case, it was the magnesium. And one atom has to be reduced. In this case, it was the calcium. An easy way to remember oxidation and reduction is a little acronym that Mark Bishop came up with in our textbook, which he calls oil rig. So the oil stands for oxidation is loss, and rig stands for reduction is gain. So we already decided that if an atom's charge increases, like the magnesium did, then that means oxidation, and that means that it lost electrons. And that makes sense. If you remember my joke I told you guys before, remember 2 atoms are walking down the street. The first atom says, I think I lost an electron. Second atom says, are you sure? First atom says, I'm positive. And so losing electrons makes you positive. So when the magnesium went from 0 to positive 2, Since it became more positive, it must have lost electrons, and we know from oil rig that oxidation is loss. And of course, reduction is the opposite. Reduction is the gain of electrons. The calcium went from positive 2 to 0. Its charge actually decreased, and the only way your charge decreases is if you pick up some negative electrons. So a decrease in charge means reduction, and reduction means gain. All right, now let's try a couple of practice problems, and I'll take you through the procedure. So the first one will be the reaction of sodium and aluminum oxide. The first step is to figure out what the products are going to be in the reaction, and we're going to do this similarly to the way we did it with double displacement. So the sodium, because it's a metal, is going to switch places with aluminum. Sodium, of course, because it's in group 1, is going to have a positive 1 charge when it becomes an ion. So it starts out as a 0 and ends up as a positive 1. Oxide, of course, being in group 16, has a negative 2 charge, so that means we would need 2 sodiums to balance out the 1 oxygen. Aluminum, of course, would simply be by itself as a single atom of aluminum. The next step is to balance the overall equation. So we'll start out with the aluminum. There are 2 aluminums on the left side, so we're going to put a coefficient of 2 on the right. We have 3 oxygens on the left, so we would need 3 sodium oxides. And then we have 6 sodiums, so we would need to have 6 sodiums, and now the equation is balanced. The next step is to determine the physical states of each substance. For elements, we simply look at their color on the periodic table. Sodium is black on the table, which means it's a solid. For the compounds, we're going to use the solubility rules. Aluminum is a +3, oxygen is a -2, so the 95% rule says it should be solid. Aluminum, of course, is a metal, and it's black on the periodic table, so it's solid. And sodium oxide, sodium's a +1, oxide's a -2, so the 95% rule says it should be aqueous. Our next step is to determine who's oxidized and reduced in the reaction. So we have to look at charges for each element. Sodium, by itself, of course, elements are always 0. Aluminum in a compound always has a +3 charge because it's in group 3, and oxygen, of course, is always a -2 because it's in group 16. On the other side, aluminum by itself would have a charge of 0. Sodium, once it becomes an ion, is going to be a +1, and of course oxide will have a -2. So sodium's charge went from 0 to +1. So an increase in charge means that sodium was oxidized. So we simply put SO for substance oxidized under sodium. Aluminum went from +3 to 0. So a decrease in charge means that the aluminum was reduced. So we call it the substance reduced and simply label it as SR. There's 2 other labels that we use as well, which are oxidizing agent and reducing agent. So the oxidizing agent is the substance that causes the other material to be oxidized. For example, if sodium was oxidized, then it lost electrons and somebody had to take those electrons, and that somebody was aluminum. It's the one that took the electrons from the sodium. So we call aluminum the oxidizing agent. It was the agent of sodium's oxidation. For aluminum to be reduced, somebody had to give the electrons to the aluminum, and that was sodium. So we refer to sodium as the reducing agent because it caused aluminum to be reduced. Now notice that all 4 of these labels go on the left side. So whichever thing was oxidized is also the reducing agent. Whatever was reduced is also the oxidizing agent. All right, let's take a look at another example, the reaction of sulfur with lithium phosphide. Since sulfur is a non-metal, it's going to trade places with phosphorus, the other non-metal. Sulfur starts out with a charge of 0 and ends up with a -2, so it's going to have 2 lithium ions connected to it, and the phosphorus, of course, ends up with a 0 charge as the free element. To balance the equation, it's probably easiest to take a look at the lithiums first, because it's one of those 2-3 combinations, which means we'll want 6 lithiums on the left and 6 on the right, which means we'll need 2 lithium phosphides and 3 lithium sulfides. Because there's 3 lithium sulfides, we'll need 3 sulfur, and with 2 lithium phosphides, we'll have to have 2 phosphorus. The next step is to figure out the physical states. Sulfur is black on the periodic table, which means it's a solid. Lithium phosphide, lithium's a +1, phosphide's a -3, so the 95% rule says it'll be aqueous. Phosphorus, again, is black on the periodic table, meaning it will be solid. And lithium +1, sulfur -2 means that lithium sulfide will be aqueous. In order to figure out which substance was oxidized and reduced, we first look at each element. So sulfur, being the neutral element, will have a 0 charge. Phosphide, because it's in group 15, will be a -3. Phosphorus, of course, neutral elements are always a charge of 0, and sulfide in group 16 will have a -2 charge. And finally, to figure out the oxidation and reduction, sulfur went from a charge of 0 to a charge of -2, so a decrease in charge means that the sulfur was reduced and therefore is the oxidizing agent. Phosphide went from -3 to 0. An increase in charge means the phosphorus was oxidized and therefore is the reducing agent.